Stanford University.
Good afternoon. Next week, welcome to EE380. Next week is Bob Metcalf, followed by the designers of a cute little thing called Pleo. Also on the website, you might want to look at the website because there's an announcement for a panel talk by Daniel Kreis, who spoke earlier this quarter. Robot Games needs artists, and the USGS has an open house this weekend. That doesn't happen all the time. I mentioned last week that this week's speaker would be Professor Mike Flynn. Many of us have some familiarity with the circle of reincarnation as applied to computers and applications and architectures and things. During the recent decade or so of innovation in microprocessors, I started to notice that everything was something I'd seen before, specifically in old Stanford theses. At first, I credited the admissions process for admitting such clearly wonderful, fantastic people. Then I started to look at the signature page. And I noticed that an amazing fraction of them, like almost all, had one signature. There was one signature in common. That was today's speaker. He's pretty much invented all the modern architectures, although he didn't get credit for it. And he will, of course, give credit to others because that's how he is. Today's talk is about rethinking computation to move the good, fast, cheap trade-off by another factor of 10 or so. You'd think that this wouldn't happen anymore, but current speaker keeps doing it.
Thank you very much. Thank you. It's a pleasure to be here. I can't say this is the first time I've been in a 380 talk. My first one was, I guess Richard Nixon was president. Let me just put it that way, and a long time ago. So today I have an unlikely topic, and I'm going to dazzle you with something old, something new, lots of borrowed slides, and some blue, of course, which you see. FPGAs are not a natural thing, at least in my mind, as a starting point for acceleration, computer acceleration, computational acceleration. But they have proven very effective in the work that I'm going to describe today. First, I have to give credit to my colleagues. Now, originally, Thomas Namish of Chevron was to be a co-speaker, and he was going to tell you all about the intricacies of geophysical modeling. But one thing and another, and he couldn't make it. So I'm going to have to tell you all of the intricacies of geophysical modeling, and so therefore you're going to get a yard wide and a millimeter deep, as you can imagine. So I have a few slides on this. And I borrowed slides from the geophysics department. Olav and Bob Clapp are both up at geophysics right now, and I got some slides from them to show you about the problems that they encounter. In parallel processing research, in any kind of research, I always believe that the starting place is with an application. This thinking pure thoughts, when we go out and we're going to have a new concept, really doesn't get you very far. I believe that if you really want to do some new thinking, you have to sometimes throw out the old and start with an application, start with a problem, and build on that problem, build on the insights from that problem. So, I came into computing a long time ago. And my first the experience, I'm going to give you a few slides about this, was the genesis of something called design automation. It was really the way computers could be realized in a reliable, orderly way. And of course, it made an immense amount of money for IBM at the time. So let me start with that. I gave some of these slides at the Computer Museum a few years ago, so even that, it's an old talk, but I have some conclusions which are relevant to today's situation, I think, as far as achieving acceleration is concerned. As I joined the computer business, this is just a little bit before I joined, computers were built like radios, all hand assembled with a production line, and if it worked, it worked. If it didn't, it didn't, and you had to fix it later, okay? Now, there was a great movement at the time to step back and redo it right. Throw it all away, basically, and to start over again. And this was a technique based upon a few standard cards, which would be automatically produced, automated. Everything in this, the placement of the components, the soldering was all going to be automated. And in fact, it was going to take one step further. This is an ECL. IBM had invented ECL right at the same time. And this is an ECL circuit. And you'll see a little cap, these irregular silver strip in the middle. That's called a cap cut, caps. And you cut the cap to reconfigure this standard card. You can make various combinations out of it by cutting the cap in different ways. So you had a very small number of these cards, but because of the cap cuts, you could configure it in a variety of ways, not unlike FPGAs, but I shouldn't say that. Now, one of the most impressive things that they had at this time that I really liked, and looking back on it, is a simple idea. And yet, if backed up with the right depth, if you will, of support, it had an amazing effect. The designer was given these sheets, like transparencies, with a little box on them, and you would put down the type of card you wanted, the logic function, and you could place it in a socket or you didn't have to. And then you just draw the line to the next circuit you wanted to incorporate, the next logic block. Okay. Overnight, these sheets were taken, and for each block, a punch card was made up. Then the machine, an old IBM 650, would go through and route and place the cards. And they would be put into sockets like this. These are 8 cards to a socket, and there'd be 3 of these plastic sockets in a row, and there'd be 10 rows to a panel. And the machine would wire wrap. These are square pegs coming out of the end of the sockets. And an amazing Gardner Denver machine. Oh, it was like going to Hollywood and seeing these, a ballet or something, with these machines. We just whip these panels around in milliseconds and wire up the frame. And so it'd be done automatically. And then with a bed of nails tester, you knew that it was right and it was done. So all you had to do then was populate, put cards into the frames, and 4 panels made a page, 4 pages made a frame, and 1 or 2 frames made a computer. And you could sell these computers for $3.5 million, so, because they were priced on the basis of the old way. The radio way with all these people soldering. But in the end, it was, how shall I say, pure gold. And they worked. That was the amazing thing, of course, because of the automation. They worked and they became the dominant scientific machine of the day. Now the message, I had several messages. One is simple sometimes. Everything was simple. But it was properly supported. You went out and they bought these big Gardner Denver machines. And it was a new beginning. And IBM actually threw all this away to do it even better with a new generation of Ford System 360, which was coming on in just a year or so after this. So, that's a look back. Now I'd like to see where we are today, and I'm going to try to give you some alternate ways of thinking about the problem that we face today. And the problem, of course, is dealing with large-scale multiprocessors, or multi-core, multi-threaded, blah, blah, blah. Okay. Today, all of the alternatives have faded away. Okay. As you can see, this scalar approach, which is multi-core approach, dominates the at least the 500, if you will, large computer installations in the world. For better or for worse, the variations have gone away. Now, what I'm going to argue for today is a different model of hardware and a different model of software. Okay, that's nice. To throw it all away, basically, and start over again. In that sense, FPGA is a reasonably good starting point because it's an emulation technology and allows you to do a lot of interesting things. So, but the applications I'm going to look at are obviously the ones that are simplest to deal with. Now, they can be memory limited or compute limited, although I'll have some caveats about that later. Generally, they're static in control structure, although they can be reasonably dynamic as long as they're not too big, as long as I can contain them, get my arms around them. And of course, we're going to talk about a core plus accelerator approach rather than multi-core. Okay. Now, you know, every step in the evolution of the processor sort of, you can get into these situations where every step made sense, but where you are at the end doesn't make sense. And I claim for many of these applications that that I'm going to describe, the allocation of a lot of silicon to things like cache and buffers and branch predictions, all of that is useless. And the only thing that counts is the arithmetic. And we don't build machines that way. Although for many applications, they're forced to use what's made. And so I'll talk about that. The alternative is what I will call a structured or a systolic array. And I'll define exactly what I mean as we go through this. But it's generally, you could think about it as something which, like a GPU, FPGA, or anything specialized piece of equipment that supports streaming to a large degree. Or it could support it in an array fashion also. The goal is to avoid going back to memory, because many of these applications are memory limited, and so what you want to do is do a computation and then forward it to the next stage that will continue the computation and continue that process until you get an answer, and then finally only return a complete result. So if you can do this, you can get some significant improvements in overall computational speed. Now, from 100 yards away, this is the idea. We're going to take a computation, we're going to unravel it, find its data flow, and we're going to pipeline the computation until the silicon runs out, okay? And in order to avoid, since these are memory-limited applications, in order to avoid going back to memory, we're going to have a big buffer so we can hold the intermediate results, and then we're going to choreograph them back into the array so that they'll be available at the right time in the pipeline. And if we can do this properly, we should get some big speedups because we've decoupled memory from the rest of the computation. Okay? Now, FPGA. It's an unlikely starting point because if you just look at what you have to do, you want to do an add or a multiply or something, the area time power product of a FPGA implementation of an adder is significantly inferior to a custom designed adder. Okay? Maybe 2 orders of magnitude. So it's an unlikely starting point. The thing about it is, though, that it has a lot of these cells. These are big pieces of silicon, and they have 100,000, a million cells. So that the parallelism is going to have to overcome the inherent disadvantage that we have in area time power product, which I'm going to show you is doable. We're going to stream the data, mean pipeline it, across the face of the FPGA, and we're going to minimize the memory bandwidth. We're also going to take advantage of the FPGA in at least one sense, because we're going to configure it, let's say, so that it has a 17-bit floating point mantissa, if that's only the precision we need. So we're going to buy back some of this area time product loss by configuring it exactly to the application. So in order to do this, it requires effort. And there's nothing automatic right now anyway, but we're getting there. I'll show you some of the tools we have. Now, starting with the first approach is that we're going to use a different programming model. I came up with this term, a cylindrical model, rather than because I was trying to think of the opposite of layered model. So what you want to do, what you want to avoid is having these layers of abstraction so you can't see the layer below you. You want to be able always to understand the absolute effect on the hardware of a high-level choice, even the choice of algorithms. So I call this sort of a cylindrical approach because what you're going to do is you're going to start with a kernel and make a complete set of choice. Algorithm, data representation, the 17-bit mantissa, everything, all the way down to the routing on the die and the pin bandwidth. You're going to do that for a small piece of the application, the kernel, and then you're going to slowly expand that till you have the whole application in this cylindrical model. You program the whole thing. Now, in order to do this, you're going to have some good tools, and you're going to have to put some effort into it. So, this is another way of looking at it. Naturally, it works best if you have an application which has an obvious hotspot or a critical portion of the application that's containable, that's reasonable. So, and then, of course, you, as I say, deal with all of the choices for that piece of the application, and then you build out from there. So in order to do this, what you're going to do is basically, what I like to say it is in two ways. You're going to, first of all, create a data flow graph. And you're going to maybe repeat that graph 2 or 3 times for different data strips until the pin bandwidth runs out on the FPGA or on your memory, your DRAM memory. This is the buffer memory now. So it's sort of SIMD until the pins run out, and then pipeline until the silicon runs out. And that's the way you're going to get your performance with this kind of a model. So, and if you do it right, also, there's some tricks you can play, not the least of which is data compression. Because if you have a lot of silicon, you can compress the data as it is in memory and then decompress it as it enters the pipeline, and that's just some pipeline stages. And when you're all through evaluating the computation, you can compress it again, put it back to memory. And some of these applications are easily compressed, and it's you can make it lossless or lossy as the application warrants. Now, all of this requires effort. So I go back to 1967, and I recall this famous statement. I dare say there weren't too many of you here at this conference. This was in one of the joint computer conferences where Gene Amdahl, who enunciates the Amdahl law at this particular great debate he has with Dan Slotnick. And Slotnick is, of course, proposing the parallel processor approach to computation. And Amdahl is defending the integrity of the uniprocessor approach. And of course, Amdahl is right for the next 45 years anyway. But Slotnick, who sadly dies just a few years after this in a sad plane accident, was one of the great people of parallel processing, and a sad loss to the field. But he had a false dawn, I think, he was a developer of the ILIAC 4, as you may recall. But how much effort is too much? That's the question. And the answer is, well, if you want speed up, you're going to have to put up some effort anyway. So I'm going to tell you now about what we do at Maxeler. Maxeler is, most of its activity is based in London. And all of the FPGA development work is done out of London. So I do get some frequent flyer miles out of all this. And but so most of our customers, well, they're all over the world, but a number of them are here, especially Chevron, as my colleague Thomas Namath would have told you. And I'll quote some of his work that in a later slide. So now we do it in basically, I'll describe this in 3 different series of slides. The methodology, the tool set, and tools are absolutely important in this, as you'll see, and then the hardware. Hardware is probably the easiest thing to describe, but in order to do this properly, you take an application that looks plausible. And I can tell you, implausible applications would be applications that use all 64-bit IEEE floating point, for example. That's because we just aren't going to be able to do much along that line. It could be a huge problem that's scattered all over the place. Also, that's going to be difficult. Or a problem that's so ill-defined that it could call one program once and another program another time. Problems like that we can't deal with. Okay? So we qualify an application by looking at it before we ever touch anything. Then we analyze it, and it looks at its data flow, the static and dynamic data flow of the problem. And the next thing you have to do is transform. We have to create the data flow graph, do a data layout, and a representation analysis. This is where you're analyzing the data, and you're looking at, do you want to do 2 passes or 10 passes of the data through your pipeline, or how do you want to deal with it, and how are you going to basically deal with the bandwidth problem? Getting stuff from memory, from your buffer memory or from the original memory, the host memory, into your pipeline, and then how do you set up the pipeline to support the computation. So now we then partition, organize the data flow, meaning change the aspect ratio so that it's long and skinny rather than fat. Because then if it's too fat, of course, we won't be able to get the information in and out fast enough. So that's basically the process, and then finally implement it. The compiler will produce the runtime interfaces, and will configure give us the bitstream for the FPGA, and we'll probably have to go through this compiler a number of times before we get everything completely fit and optimized. And you know, optimization is never done. Once you do it, especially with an FPGA, you can also say, oh, you know, I could go back and I could fix this little square up here. There's a little bit of extra silicon over here. We can squeeze it a little bit more. We can do better. So it's a constantly evolving target. The most important tools we have, aside from the compiler, which I'll talk about in the next slide, is a profiler that allows us to look at the application and decide whether this is one we want to take on. A performance modeler gives us, without having to actually build the whole application, it gives us a good idea as to what we can get out of the application. How much speed up can we get out? How big is the application? How will the nodes fit on the FPGA or on our boards? And gives us some ideas of what design alternatives we should consider. Finally, there's the OS support, which choreographs the memory entry into the FPGA and the host. And finally, also, there's the bitstream. You have to manufacture the bitstream for the FPGA. Now, the compiler, we had toyed with this. We take the user application and rewrite it, basically, in Java. Well, it's implementable Java, meaning that it has to be static. Because the computation is going to be static. It's going to be realized in a data flow graph. So we have to rewrite it to fit the computational requirements. It could be in a form of Fortran. We had actually toyed with producing something which we call Fortran 0, you know, some restricted version of Fortran so that the customers could have more access, be more familiar with it. We analyze the code and then transform it to match the bandwidth. And then we have two versions of the compiler. One generates a hardware design, and the other one generates a data flow graph. I'll show you the data flow graph next. Well, first of all, the manager compiler manages basically three things. It has three blocks it has to create. The PCI Express interface, the memory interface, and the computational, the data flow graph. Our model is we're going to take a board and plug it into a PCI Express X16, and that is going to, that's the way we're going to interact with the host machine, with the host server. So there's an existing host server, we plug in our board, for example, and we get the acceleration on the application. And the host is there for whatever reason, maybe to help us, maybe just to stage other information, or maybe to do another application. The compiler has to, for us, manage the PCI Express interface, our memory controller. We have memory on our board, the buffer memory that I talked about earlier, and of course it has to manage the arithmetic computation. So these can be in different, and frequently are in different clock domains. Memory is operating on its clock, PCI Express is operating on its clock, so we have to be able to operate between these clocks and bridge these streaming blocks with different configurations. And it also has to change, the compiler is going to change the aspect ratio of the data flow for the arithmetic computation. In other words, again, if the data flow comes out big and fat, we have to squeeze it down and make it long and skinny. Here's a data flow fragment that we would get out. A series of adds and subtracts, I don't know whether they're visible there, some constants. And so this would be an early version of what we would see in one small portion of the graph. Later on, we have to put, these are FIFO buffers, which are going to synchronize the inputs to the various nodes. So they're going to happen, you're going to get the right data at the right point in the pipeline. Okay? Now, this is what an actual data flow graph looks like. 5,000 nodes. This is a complete application. And it's about 250 long by 100 high. So you do need tools to deal with this. You're not going to deal with this by, hand analysis. We did in the beginning, we did, but now we are to a point where we have some pretty good tools where we can take, this is an actual application. We can take applications like this and squeeze them down, arrange the inputs for them, and achieve the acceleration. Now, when you have 5,000 nodes, 4,800 nodes, and each node is active doing a computation every 4 nanoseconds, which is the cycle time of the FPGA, you got some real power here. Okay, so this is how we get acceleration, basically. This is the secret. And what you see is a data flow graph, but really it's going to become a systolic array. And because of the FPGA's nature, it's not limited to nearest neighbor. And remember, it has very good communication possibilities. Because of that, we're able to create an unconstrained systolic array over 4,800 nodes. And so, that's the argument for FPGAs. The kernel compiler takes the data flow graph as input, it transforms it, optimizes it, put the buffers in, and gets a structural hardware design out, VHDL design, which is then taken by another tool which creates the bitstream, and of course you can then reconfigure this later if you need to. We basically have a card, which I'll describe. Let me go to the next slide first. This is the little board of the card. Fits into a PCI interface. Uses 2 of the biggest Virtex Xilinx chips we could get. 24 gigabytes of memory, and a 10 gigabyte FPGA interface link between the 2 FPGAs. So you can run the pipeline from one into the other if you need to, and then continue the computation. If you're running out of silicon on one, you can bring it into the other. And the operating system has Linux device drivers which manages the plumbing, the choreography of the moving of the data back and forth. Now, there's a card, which I just described, and there's a box which has either, it can be configured in 2 ways. You can have 4 of these cards, or 1 card and a 1U server. And then if you have 4 of these cards, then you're going to take this will plug into a PCI Express on another 1U server, and so you could have 96 gigabytes of memory in one of these 1U boxes. And then, of course, you can put a rack of these together. Let's talk a little bit now about an application, Seismic application, which I don't know a lot about, but I'm learning. It's an amazing field. For one reason or another, my grandson has decided to major in geophysics and down at UC Santa Cruz. So it's interesting, and I'll describe more about the various things that are done, but mostly it's coming from physical data. The data you're using is physical data, so it's not 64-bit IEEE floating point. It's stuff, reflection, noise, whatever it's coming from. A typical application is finding oil or gas. And out at sea, you do this with these sensor grids, and you're impulsing every 10 seconds, and you have 30,000 sensors to record data. So you get a lot of data very quickly. This is a slide I got from Olaf from Schlumberger, and shows a boat. And these things are spread out as if they were over the city of Oslo. Oslo is a big center for these marine exploration boats, ships. And this shows 6 kilometers is the string length, and about 1.5 kilometers across. And the boat, as again, just tugs it all along, and it looks a little bit like this. Well, these are the streamers, and these are the recorders. So you have, and so this is what the boat is dispatching as it. You can have these an offset as long as 10 kilometers. That's a distance down, and you can have these recorders will be every 10 to 20 kilometers. They'll be about, meters. There'll be about 30 to 100 meters between the streamers. Now, it is important to get a lot of points. Now, I'm going to tell you that this is done with low resolution, and you can see nothing. This is done, and it would give a geophysicist palpitations because he can see something with this. Now, what is he saying? Somebody had to explain it to me. What you're seeing are these fractures. You see these little lines here? Those are the fractures, and that's what's important to the geophysicist. And so if you can't see them here, it's a useless run. You have data here which is useless to you. So this is why you need high resolution, why the number of points, and this is these are three-dimensional objects, of course, that you're creating, are very important. So you need to process a lot of data. So now, at this point, we're doing reverse time migration, which, and I'll tell you a little bit about forward modeling, which is a part of this in just a moment. I'll give you some data from our experiments, actually the Chevron experiments. But beyond this is something called the gold standard of all this, full wave elastic modeling, which is 100 times more computation. So there's no shortage of computational need in these applications. As you can see, just looking down here, a survey, that's a day's work, creates up to 500 terabytes of data to be processed then by servers which to date have had up to 10,000 nodes, 10,000 one-use servers basically, and the runtime is days to weeks. Intel does like to go down to Houston. This is where all of these are, and the power company in Houston just must love it when they turn on the 10,000 servers to do a run. Interesting enough, in geophysics, oil and gas, of course, water, climate, these are all characterized by basically the same sorts of mathematical problems, and this wants to slip away from me. When you borrow other people's slides, you never know what happens sometimes. So in any event, they all have a common set of mathematical properties, and generally the input data is constrained by the recording, and so it's not high precision. Now I'll tell you a little bit about some work that I can tell you about, because it published data on using FPGAs and for acceleration. Forward modeling basically is simulating wave propagation through a solid from source to receiver, and you're comparing it to recorded data. So you have all these sonic booms. You've figured out how far it's taken. The frequency that you're recording varies from about 7 hertz to high frequency 25 hertz. So it's in this very low frequency range. And you're looking for interesting things down there. Now, on a Xeon, this is what happens. Basically you're doing three one-dimensional convolutions and to figure out the shape. And so if you were to look at this and just look at the density of whether all the cycles are spent and the number of flops, you can see a couple of things. You're doing 2 load stores or branches for every flop. And if you look at it in general, for every flop you're getting a miss rate per flop now, not per op. This is the total data cache miss rate, but per flop it's about 10%. And you're getting a CPI of about 1. So, now, comparing this to FPGAs, the Xeon is 20 times faster, let's say. Let's say it achieves a 4 gigahertz rate. But, so the problem then for someone building an accelerator is you have to compensate for this inherent advantage. Now, this is data from Thomas's work, who was using our system that we installed at Chevron. And the lower line is a Xeon, and the upper line is, of course, the lower line is in time, is the FPGA, and the upper line is the Xeon. So, interesting thing to observe was that as the problem gets bigger, the resolution gets better, the FPGA, the accelerator, gets better. And the reason is because not so much that we're doing better, but we're scaling up. And the Xeon is getting more cache misses, data misses. It's not scaling up. So it's getting slower, basically. Now, at this talk at Las Vegas in November, it was interesting, and I didn't copy down all of these things, but Thomas gave his talk, and he quotes this data, and he had a colleague from Houston who had done the same thing on a GPU. Same problem, exactly the same problem. And the results, I don't remember exactly what the results were, but they were like this. He was getting about 20x speed up on the GPU. This is an NVIDIA GPU. Only he couldn't scale it up to, in other words, to high problem sizes. He was, at that point, he was unable to go beyond maybe about 400 points, 400 cube, because of memory limitations. So now, it was obvious, with a little discussion that the GPU approach is going to be cheaper per board. Our boards are not cheap because the FPGAs aren't cheap. Maybe a comparable board, let's say might be, well, it's not comparable because they're bigger in memory size and everything else, but you have to figure that they're 3 or 4 times as expensive, the board now. Also, the effort that you put into it. We put more effort into it than they did. And one thing that the customer particularly liked about the GPU approach is that his people could do the effort rather than having specialists like us do it. But I think that situation is changing as time goes by. I think we are now delivering compilers with our application so that people can make changes to the configurations. Okay. Now, in order for us to do this, we basically, to do that application, we convolve 4 points per FPGA. That's to say, like we're doing SIMD by 8 through the application, compared to the Xeon. And we have a pipeline of 468 stages. So you do a little arithmetic and you say we're doing almost a teraflop, because we're doing 8 times 468 flops every 4 nanoseconds. That's not exactly true because some of these, I call them flops. For us, some of it is integer, some of it is scaled integer. We do some scaling, but because we know we are controlling the nodes and what they do. And some of them are true floating point, but usually relatively low precision. let's say less than 24 bits in mantissa. And occasionally there are, dead nodes too, nodes that we can't profitably use. So from a 10-yard away approach, this is the system. We have a 192-bit DDR. This is like 6 channels of DDR, 6 times 32 channels of DDR coming into the FPGA, single FPGA. We have another FPGA on the same board, and then we have the operating system controlling the choreography, I'll call it, the data movement between these two FPGAs and the memory, and the 6 memory channels. And then, of course, the host CPU is doing something too. So this is another way of looking at it. This is sort of the data flow graph in the middle. And just do the arithmetic, and you can see that you have probably a maximum speed up of about 374, of which we realize about 240. So operating at about, as I say, 1/20th the frequency and 50 to 75 watts per board. So now, how typical is this? Well, first of all, I'll tell you that forward modeling, reverse time migration, and a number of other things in the seismic community we've done reasonably well on. It's typical of what we do. We've also had a number of successes in the financial community. Let's say high frequency trading, arbitrage, Monte Carlo simulation, derivative pricing of all things. It's easy to get good speed up on a CFD, but again, unless CFD needs very high precision. So if you need the full 64 bits, that uses up too much of the FPGA silicon. On the other hand, if you could use a lattice approach to solving a CFD, then of course we're back in business. Image processing, medical image processing, medical records, X-rays, etc., should be no problem. So those are typical applications, and I think that reflects pretty much where we are now and where we can go, where we really don't feel comfortable going. And there's been slews of academic studies where people have come up with random number generation and let's say crypto applications, etc., which is well known that you can do these on an FPGA very rapidly, if you really need to. I don't know how many keys you have to analyze, but if you did, this is the way to do it. So now, this was a problem that I had to wrestle with when I got through and I looked at this and I thought, my goodness, what does all this mean? How can you take a technology that is, say, 100 times inferior to a custom technology, and a lot of smart people have worked on this custom technology, producing these 8-way or 4 cores or 8 core chips. How can you beat it by, let's say, 50 times? Remember, I was quoting in my data like 240 was reference to one processor. Now, in fact, when you put 8 processors together, you generally get a speed up of about 4 for the conventional, for the, let's say, multi-core approach. So realistically, die-to-die or board-to-board comparison is we're getting maybe a speed up of 60. So, but if you look at the die, the x86 die, you'll see most of it is covered with cache and buffers and branch buffers and this, that, and the other, which are not needed. I mean, for these kinds of computations. And I submit to you that there are many computations like this that don't need all of this. And so this is where I say we sort of evolved, and each step in creating the modern processor die made sense. But if you look at it from these application points of view, and you look at it, the result doesn't make sense. There's a mismatch here. Each step made sense. Result may not make sense. Secondly, this is the slot-neck problem, the lack of robust parallel software. And part of the problem, I think, is this notion that, again, layers of, let's say, non-transparency. You want to be protected, insulated from seeing below this layer, this beautiful layer of the program that you've created. And of course, this limits what you can do, limits the trade-offs you can make. So it's a combination of these two things which really sort of limit the traditional approach. With good tools, and we are getting better, as I say, with the tools, we can create large systolic arrays with surprisingly good area time power. Overall, it's quite good. In the small, it's pretty poor. But when you put them all together, when you get those 5,000 nodes all hopping on the same foot every cycle, it's pretty good. You do need effort, though. So, are we there yet? Well, no. Slotnick promised it wouldn't be easy, and he was right. But we're making progress. As I say, I think within the next few years we can ship things like Fortran 0 or compilers that customers could actually use. I'm also hopeful that we can come out not only with new ways and new tools, but perhaps a new idea of looking at hardware. If FPGAs are too, let's say, atomic, a computational node, a starting point, what would be a better node? Okay? Maybe a small processor, maybe an adder or a small multiplier, maybe an array of these would be a better starting point for true acceleration for many applications. Okay. Finally, acceleration-based speed up using systolic arrays is possible now. We need to give attention to the memory or arithmetic data representation, streaming, and RAM. And you can get lower power with non-aggressive use of the frequency. A programming model uses cylindrical model, but speed up requires lots of low-level program optimization. And good tools are golden. So thank you. Any questions? Yes, please.
So since the FPGA board is 75 watts,
Yeah.
and that's, you said it's like 60 times faster than 4 processors, but as an operation per watt, it's probably much more.
Oh, yes.
200, 300 range.
Sure, right.
So much more power.
Yes, absolutely, absolutely.
Using all of the silicon.
That's right. I'm using all of the silicon. But it's, again, if we had a more efficient atom to deal with, computational node, we could really do something splendid. Question, yes.
Yeah, so far, I came in a little bit late, so you may have touched this at the beginning, but you've dealt with some very specific kind of high-performance computing-related applications where people were willing to, I assume, spend an enormous amount of time and money to optimize for these problems.
They were not willing to spend an enormous amount of time and money because we spent the time. They didn't do it, and they didn't give us an enormous amount of money.
But I mean, as, you know, say somebody here was working on a research project and wanted to build, you know, had a computing project they were working on and could not, say, hire your company to do this. How hard would it be for them?
Well, now, you see, we're, as I say, we're a few years away from that. We're moving towards that. We have the compiler now, and we can ship the compiler with the board, but usually we have to do the initial design for you. We're at that point. Now, if you were very sophisticated, you know, I don't know, maybe you could, and we gave you the rules, you're going to have to rewrite your application in Java, you know, and this is an executable form of the Java, so it can't have any dynamics to it, you know, it has to be a static thing. You could, but there's a lot of tricks. And, but you would get the operating system and you'd get a lot. You probably wouldn't get the speed up that we could get. That's the downside at this point. In fact, but, you know, sadly enough, if you really want the best speed up out of a GPU, you better have an NVIDIA fellow there too to help you with CUDA, you know. So you don't, this is Slotnick's law, you know, without effort, you don't get too much.
What do you think the time difference is between, say, your company doing this and what it would take for a programmer to just write a standard version, hack one out in C or something?
Well, we do this in typically 3 to 6 months, you know. So, I mean, you have to think in those terms. I suppose if it was a crisis, we could do it in 2 months or something like that. But generally, in that kind of a time frame is a typical time frame that we quote. Yes?
Yes, do you reconfigure the FPGA on the fly?
Yes, we can. We don't generally do that, but we can do that. It takes 100 milliseconds, I think. And we have a path on the board to do that.
Second question, have you considered long precision integer rather than floating point?
We can do anything, you know, it's not, the only reason I said floating point, we do floating point. The problem is that there are so many people out there building big floating point multipliers that it's hard for us, you know, to say, you know, hey, if you really needed a lot of floating point multipliers, there's just so much out there, especially in terms of GPUs, which probably will do the job better for you.
The GPUs are pretty bad at 64-bit. The GPUs are pretty bad at 64-bit. They're reasonable 32.
That's right. Well, I'm sure it's coming in the next generation. Right.
Only 4x to get.
Yeah.
Mike, isn't the advantage of the current Maxeler approach, however, the fact that you've done it before, you have a library, you have the specialized tools and some back pocket algorithms for managing things like data transfers in compressed form?
Sure, but a lot of that is also built into the compilers. So they come out automatic, you know, so that's what I was saying, that we're moving towards the ability for a user to be able to deal with some of this themselves, to a point. I mean, there will always be a point beyond which, you know, Slotnick's law clips in, and you have got to put some extra effort in. Yes?
Comment about how it compares to Synfora, the Pico tool.
Say again.
Can you comment about how how Maxeler compares to the solution of Synfora? I think it's called Pico, where they basically try to compile your, as I said, the non-dynamic application into ASIC and basically tape out a chip based on your.
Okay. You know, Altera has an approach called hard copy, where you do with the FPGA, and once you're happy with it, you take that design and then you make an ASIC out of it. Xilinx had that at one time. It no longer supports that. We found for other reasons that, but in principle, that's doable. We found that for other reasons, mostly to deal with pin bandwidth, etc., that the Xilinx chip is a better starting point than the Altera. But that's certainly a very nice feature of Altera. So you can you flush out your design, you make sure it works properly, and then you say, give me the ASIC. Then, of course, you can't change it. You're sort of stuck with it. But if that's all you want to do, that's fine.
Like when you look at your Seismic application, did you look at porting back the parallel algorithm to a serial version to see how much the algorithmic changes made a difference versus the hardware acceleration, et cetera? In other words, I'm sure the algorithm, by the time you got done, there were quite a few minor differences.
Yes. Now, let me tell you
Sure.
that for us, we always take the customer's source code,
Right.
and that belongs to him.
Okay.
So we work with the customer to, on the algorithm,
Right.
but it basically belongs to him, and it's only done basically after, we've agreed on the best algorithm. So we don't come up with new algorithms,
I'm not
basically.
saying you do. What I'm more worried about is a lot of times what people will do is they'll have a sequential application, they'll build a parallel implementation, and along the way, they'll make a few minor changes. The minor changes make dramatic difference in the performance, and if you want to do an honest comparison, you wind up finding that you're a little bit embarrassed. Because you find that the speed up wasn't for where you thought it was.
We haven't done that because, you see, we're working basically with a data flow graph.
Right, yeah.
So, and we've optimized it, but it's mostly for our purposes to fit on the FPGA.
Right.
Not so much that we worried about the
I don't think it's
Xeon.
intentional. I think it's what happens. It's one of those things that happens. It's kind of like you said about creeping incrementalism and so on.
Right.
It happens when people do these things, and I've run into a number of situations.
Yeah.
And it's just really embarrassing because you say, "Oh, I've got this fantastic parallel speed up and this and that." You say, "Well, I'll tell you what. Why don't I just take this now? I've got this new, modified algorithm, put it back to a sequential implementation. Whoops, it's faster." I'm a firm believer that when you look at speed up, you shouldn't look at the parallel algorithm on one versus the parallel algorithm on N, say. What you should be doing is you should be looking at the best sequential implementation of whatever the modified numerical method is.
Of course, that's the definition of speed up. I mean,
That's what it should be.
That's
It's not
absolutely
it's not
right.
what people use, but it's what they
Yeah,
use.
well, I mean, we just do the best we can as far as this is concerned. And at the same SEG conference that I talked about before when we were presenting our data, there were several other approaches mentioned, and one of them was just simply hand optimize the hell out of, these routines. And the claim was that he could get 5 up on the compiler, basically, by hand optimizing. This is the best compiler that we could find, the best one that was available for the code, but the claim was by some other person that, yes, he could, by hand doing the code, he could get another 5x on the code on the same Xeon. True or not, I don't know. So I just report that
If
to
you
you.
want to hide that and claim it's something else, you just tuck it into the compiler,
Yes, of course, right.
and then it becomes something
Well,
else.
You say cookie necessity.
Yeah.
Yes, please.
Actually, 5x seems a little strange because the Xenon is not a 5-way processor, and if you're at 1 CPI already, then how do you get to 5? But
No, they're going to remove instructions. They're going to, just as you say, it's going to be a different program when they're all through.
I mean,
It's not
the
the
biggest thing
same
that happens is the convergence criteria. What people will do is they'll do these algorithms, and they'll say, "Oh, I'll do this thing so it only iterates a certain number of times," or the convergence has this little hack here. Well, this is a completely different numerical method.
Right.
But actually, my question was, how much of this is actually due to the fact that with FPGAs, you have a very different ratio of, for lack of a better term, instruction decode versus arithmetic?
That's right. No, I mean, these are going directly, this is a systolic array.
Yeah, I know. Usually specify instruction. There is a tiny little thing that looks like specify and add, do and add,
Right.
specify and add, do and subtract, or specify, subtract, do, subtract, et cetera. There is something like instruction. There's operation specification happening. And with the FPGAs, you have a lot more operation specification bandwidth compared to your operation
That's right.
bandwidth than you do in processors where it's 8 bits of instruction and then,
That's right, it's a much more general model. That's why I said at the beginning, maybe it's time to rethink some of these things. You know, and at least the FPGA, you can look back at it and you can say, you know, we had a broad tablet to play with here. You know, we could do a lot of different things, and maybe it's time to learn from this, you know, and rethink some of our hardware models. Yes?
From time to time, people have suggested that maybe you should put a little FPGA coprocessor right next to a CPU on a processor.
Right, some people do that.
Yeah, and which of course leads to the exact same architectural issues you have here, that you have to try to somehow or another take somebody's source code and run it on this FPGA. Have you guys looked at that at all?
No, well, actually, the Xilinx pieces have embedded processors on them.
They're kind of the opposite way around.
Right, exactly right. No, look, if you have 5,000 nodes, we're going to need a lot of silicon. You know, so that's, the more silicon we have, the bigger the problem we can handle. Ruby?
So I had a comment and a question. The comment, of course, is that if you want to do an application-specific computer, it can be faster by any amount than a general-purpose computer. And of course, you know that. I mean, the question is really, the interesting part, it seems to me, is the partitioning. Somewhere along the way you said, when you made your cylindrical computing, you had a bunch of long, narrow pipes.
Yes.
And I think what you want is you partition the data into, say, some number of pipes.
That's right.
And that's the interesting intellectual question. Because if we could partition the data into these small chunks, they will fit nicely on multi-core, many-core chips without missing in their first or second level caches. And they won't communicate with each other, you know, so they would be perfectly linear parallel.
Yes, exactly. In fact,
So
why have these
how do you
caches?
partition?
Take the caches out and put in more processors.
Well, you know, you may not need to put in more processors because the caches take the place of replicating logic in the FPGA.
Well,
Okay, you instead of replicating the logic, you save the intermediate results and reuse the logic in the process.
okay, well, let me just respond to your first comment. And the FPGA, I mean, you create, every time you do write a program, you're creating an application-specific something. And the FPGA is application-specific for that application until you reprogram it, until you put a new program in. You can put a new program in 100 milliseconds. So it's as general purpose as, you know, general purpose computing is.
I think not quite. I mean, basically, you're taking a subroutine and you're saying instead of implementing the subroutine in software, let me throw it to this FPGA. And so it speeds it up a great deal. And the new programming paradigm should be, it doesn't matter whether you're speeding up this subroutine with FPGA or with another core or 5 other cores. So I mean, that part we don't need to argue, but I think related to this other gentleman's question is whether you implement your narrow pipes on FPGA or something, the trick is partitioning the data.
Oh, absolutely.
And if we knew how to partition this data, we will also have much better performance on multi-cores and many-cores, you know, the general purpose variety.
Okay, you know, so there is a failure of the programming model. Because our programming model forces us to do that.
You may, for example, in Maxeler, have found a way to partition the data, and that's the holy grail.
Okay, well, there you go. Who knows? Maybe we found it and didn't know it, so there you go. One last question.
You mentioned towards the very end that you were thinking about, you were starting to look again at, well, FPGAs you said were horrible, except that they work really, really well.
That's right.
And And he said, well, why don't we go back and think about, what would better nodes look like than FPGA nodes?
Well, the FPGA is a configurable logic block, is a node. So, but we generally never go below an adder, something like that, 4-bit adder, something, who knows, I'm willing to, to take a look at that graph there and say, well, now what are these nodes? What are they doing? I just think that it's a question, and I throw it out there. This is a seminar for you guys to come up with new ideas, and I'm just here as your reporter telling you, here, this is what I've seen, and now you guys go out and come up with these great new ideas. Yes?
So let me restate what your challenge here is. You're thinking that you need to have something that's where the incremental unit of action in a configurable device is something other than a gate.
That's right.
And I think that makes a lot of sense. If you have a lot of silicon, you can put a lot of small, not very smart processing above the gate level on the parts. So you need a field programmable something array.
That's right.
Mike, talk about ancient history. Remember ULMs?
Yes.
How many years ago was that?
Oh, I don't know.
Is there anything from that that's useful for the present day?
It was too small.
Yeah, too small.
I thought, yeah.
What is the resource that you typically run out of first on the FPGA? Block RAM versus DSP-48s versus...
It's a choice between pin bandwidth, pins, and silicon. But usually we can figure it out so that we'll run out of both at the same time. So that's the goal, And if you get a bigger FPGA with more silicon, well, then we would restructure the problem in a different way. So we're always going to try to use it all up.
So making sure I understand, each problem then ends up with a different level of height and width.
Changing the aspect ratio, that's right. Changing the aspect ratio, unrolling it, making the pipeline deeper.
You mentioned critical section.
Yes, yeah.
Sometimes when you're doing this unrolling, you turn one critical section and invent another.
Well, it could be, but these are fairly static problems. Well, in any event, look, I can tell you I'm your reporter here. My colleagues do this all the time. I'm not the one that goes down there and chips on the bits,
If you look at his algorithm for seismic processing, there's not going to be a lot of critical connections.
Yeah, it's all straight through.
It's all straight through, and it's never one-dimensional convolution. So it's kind of like, pretty ideal problem for the situation. And the other thing I think that Mike sort of alluded to and came up with the other questions, there's really no instruction, and the person said about instruction selection, there's really none of that going on. That's been compiled by the structure of how the pieces are connected together by the conductivity.
That's exactly right.
Except for the FPGA is completely programmable, so it's reading a bit and saying, what do I do?
No, not at all. You got it completely wrong. All that happened was
The table is set.
Yeah, right.
And so it's going to do this.
Right. It reads, and it reads the inputs, and specifies the output from reading the input.
That's right.
And and that's actually, it is actually a decoder because you programmed it in.
Well, you have to, in fairness to you. It's wires. Yeah, it's right, but it's wires. You have to look up in the table. In that sense, this is the instruction. You're looking up in the table. Okay, folks.
Thank you.
For more, please visit us at stanford.edu.